We're now going to look at Kirchhoff's voltage law, which again, it's also abbreviated KVL, so you're going to hear me use KVL as opposed to always saying Kirchhoff's voltage law. And then we're going to do some examples for this. Now, Kirchhoff's voltage law deals with loops. You can recall that Kirchhoff's current law dealt with dealt with nodes. KCL dealt with nodes. And in this case, KVL is dealing with loops, which of course is why we had to first talk about what a node and a loop is, because KCL and KVL require us to understand what a node and what a loop is. Now, Kirchhoff's voltage law, there's really just one version of it, and basically here, you might be able to even guess what it is based off of what the KCL is, but the actual law here is that the sum of all the voltages in any loop is 0. And that, again, I don't think should surprise us too much. It's kind of parallels what KCL is. And to give you a quick example here, and that's what we're going to do, is we're just going to look at a couple examples here. I'm going to start with a very basic, really basic circuit here. So this very basic circuit here has just got two voltage supplies and a resistor, I'll call it R1 here. It's got some voltage across that. And we're supposed to find what that voltage is. Now some of you might say, oh, that's an obvious answer. But let's go ahead and apply the voltage law, KVL here. So we have to do a loop. Now in this case, there's only really one loop in this circuit. Remember we said in the previous lessons that loops, there's often more than one way to do a loop. And in this case, we can see, the loop that we have here is basically that loop right there. Now, we always said it's important to give an arrow to the loop. We need to have a direction. And that's what we do here, is we're now going to sum all the voltages, but we're going to use this arrow as the key as far as whether I use a plus or a minus sign on it. So I'm coming in here, and I always start with my independent power supplies, and for no reason other than that's just what I do. But if I take this loop here, the arrow is pointing in to the negative side of that power supply. So that means I would have negative 5 volts plus, and I'm just putting it in parentheses to emphasize, there's no other reason than to emphasize the fact that this is just one of the voltages we're summing. And I continue going on this loop here, and I see that the arrow again is pointed into the negative side. So this would be plus negative 7 volts. And then I continue on here. And now I'm hitting the positive side of Vx. So it's going to be plus Vx equals 0. So that's why the arrow matters, because the arrow matters because it determines on if we hit the negative side or if we hit the positive side. That determines on whether we're going to have a negative or a positive in front of the term. So we've done our loop now. There's no other components in this loop. So that's it. And now we just have a very simple equation to solve. And we can see just solving this, I'm not even going to bother showing you the word, that we get Vx is equal to 12 volts. So we get that the voltage across that resistor is 12 volts. Alright, now let's look at a little bit more challenging question here. And this one's actually I wouldn't say it's, incredibly hard, but it's definitely a more challenging circuit here. It's going to look a lot more complicated. I'm having problems drawing my resistors today. So it's going to take me a second to draw this. In fact, what I'm going to do is I'm going to pause the video while I draw this, the recording, while I draw this all out. So there's going to be magically the circuit appearing here, and then you could pause the video to sketch the circuit out. Okay, so now magically the circuit's done as far as being drawn out. So you might want to pause the video so you can draw this out in your notes. I'm going to go ahead and write down a couple of other information here. What we're supposed to do, we're supposed to find VR2 and V2 if VR1 equals 1 volt. So they've already labeled a lot of voltages on here, but we're supposed to find VR2 and V2. So I'll just kind of underline or circle. We're supposed to find this VR2 and this V2 right here. And then we know here, I'll go ahead and erase this VR1 because we know that VR1 is 1 volt. Now, this is not a problem we're going to be able to do where we draw just simply one loop here. Sometimes you're going to have to draw multiple loops. Now, if we look at it here, you want to draw loops so that you can see, well, hey, do I have any unknowns in those loops here? And so you can kind of try and tackle any one that you want here, but I'm going to show you a loop that we really wouldn't want to use as far as finding something. If I did this loop right here, and if you want to include this in your notes, that's fine, or if you don't, that's fine as well. But if I include that loop right there right now, I would wind up with the equation minus VR2 plus 7 minus 9 minus V2 minus 3 plus 1 equals 0. And while there's nothing wrong with this equation is 100% correct. The issue is now we have an equation that has two variables in it, so we don't know two things. We can't just simply solve this. Now, when we get to some of the more advanced circuit analysis techniques, we're going to wind up with that situation all the time. But what that would mean is I'd have to find another loop to write an equation down. Now, the reality is it's not necessary to use this particular loop. So let's just get rid of this equation here, and let's really analyze what is it that we are trying to find here. Okay, we are trying to find VR2. That is one of the things. In fact, that's the first thing it says. Let's look at a loop that contains VR2. There's actually two loops that I can see that would be easy to draw contains VR2. Of course, there's this loop that we drew that we said doesn't work, but then I can see, well, wait, I can draw another loop right here that contains VR2, and not only does it contain VR2, but it also only contains 3 circuit elements, and we can clearly see that I know 2 of those 3 values already. So finding VR2 is going to be simple. So if I write my equation again using the arrow, so if I follow this arrow, the arrow is now coming into the plus side. So this is what's going to be a little weird here. I'm going to emphasize that it's plus, but because it's coming into the positive side of this, but then what's the value here? Negative 8 volts. So there's still a positive there because I'm coming into the plus side of the voltage across this resistor, but that voltage itself is negative 8. Alright, so I'll erase that plus now. And then I'm coming into the minus sign of this power supply. So that means I'm going to have a minus coming here. And what's the value of that power supply? That's 12 volts. And then continuing on a little bit more, the last one here, continuing on into that circuit element, we get that it's going in on the positive side, so I get plus VR2. And now I've gotten all 3 of my circuit elements, and so this is equal to 0. And so we now have a very simple equation, and we can solve this, and we should get VR2 is equal to 20 volts. Now we have one more unknown we have to find, and there's actually, I'm going to erase some of these loops right now just so I can clean up the diagram a tiny bit. There's actually two loops that would be equally valid to use to find this answer. So I'm going to do both of them here. The first one I'm going to do is this loop right here. I now know what VR2 is. VR2 is 20 volts. Now again, being careful, I'm coming into the negative side of that. So that means I have negative, and the VR2 itself is 20 volts. Then I'm coming into the positive side, so this would be plus 7 volts. Continuing on, the arrow's coming into the negative side, so that'd be minus, the value is 9 volts. And then I have the negative side, so this would be minus V2. Coming into the negative side again, so this would be minus 3 volts. And now I'm coming into the positive side, so that would be plus 1 volt. And this is all equal to 0. Now I clearly see I have one equation with one unknown here. And just doing the arithmetic, which I'll write it out a tiny bit here. My brain is not letting me do this all in my head right now. So we have minus 20 is 17 plus 7, so it's minus 13, minus 22 volts, minus V2, minus 3, plus 1 equals 0, and that would then be 25, so we'd get 24 volts. And of course, you can use a calculator to verify that. But I said that's not the only way we could have done this problem. If I look here, there's another loop I could have drawn that gets us V2. I could have gone completely outside and around like this giant loop on the outside in blue. And I'm going to do that. I'm not going to take the time and do all of the, okay, we're entering the negative side, we're entering the positive side. I'm hoping that you're kind of getting used to that. I'm just going to write down what we'd end up having here. So I'd have a negative 8 volts, minus 12 volts, plus 7, volts, minus 9 volts, minus V2, minus 3 volts, plus 1 volt, and this should all equal 0. Now let's do this arithmetic and see if we get the same answer. We should get the same answer, and if you do the arithmetic, well, we can clearly see I'm going to get it right away because I'll just do two things here. I'm going to do this negative 8 minus 12, and that would get me negative 20 volts, plus 7 volts, minus 9 volts, minus V2, minus 3 volts, plus 1 volt, equals 0, and we can see that this equation now is actually just the same as the equation we have up here in red. So doing all of the arithmetic, we still wind up with V2 equals 24 volts. So the key reason I wanted to show you this is that it doesn't matter what loop you use as long as the loop contains one of the unknown voltages that you're looking at. Now the only thing we have to be careful again of is we really want to make sure we pick the loops that make the most sense for us to solve the problem. It's not that picking any particular loop is wrong, it's just some will be more advantageous to solving the problem than others. So that's what we need to take away from this example. So that wraps up KVL and KCL. We will be using KVL and KCL much more throughout this course. So it's going to come back, and so you might say, I'd like to see some more examples using KVL and KCL, and you will see more examples using that. So don't worry, we'll be doing more examples with this.